Okay, so now we're going to pick up with a problem that we started in class, but I just wanted to make sure to finish for you all. This is the problem of a jet striking a vane. Um, this is similar to the problem that we did as our introductory momentum balance problem, except now the vane is on top of a cart. They're saying it's a frictionless cart, and it's moving with some constant velocity, vc. This is going to be primarily a momentum balance problem, but we'll have to do mass balance here as well. So to start with, we're going to draw our control volume just to find exactly what it is that we're looking at. Remember, when we're drawing control surfaces, we want to make sure that they are normal to the flow. And so we're going to have an inlet control surface there, an outlet control surface here. Uh, exactly what this surface looks like doesn't matter too much. And then I'm going to draw the rest of my control surface like this. And remember that there is no friction on the cart, no friction on these cart wheels, and so the only applied force is going to be this Fx here, which is what we're solving for in part A. Okay, and now, so I have my control volume all laid out, so we're going to start with some assumptions. So we're going to assume, first of all, that it's steady. So that means remember our partial with respect to t is going to be 0. Second, we're going to assume that this is a uniform flow, right? So that means our inlets and outlets are 1D. Third, we're going to be neglecting body forces. Right, so for example, that means G, right? We're neglecting gravitational force. 4, we're going to be assuming that rho is constant, right, or that we're incompressible. And then fifth, I have to make some assumption about the area of the jet. And as it's drawn here and based on what I'm given here, we're going to assume that area of the jet is equal to constant. And we'll see how that works out when we work on the mass balance. So first of all, so now for part A, we want to find the force Fx required to restrain the cart. And there are a whole bunch of different forms of this expression that we can use. But since we know that our flow is steady, uniform flow with inlet and outlet are 1D, we're neglecting body forces, constant density. So we can skip right ahead to one-dimensional force balance with one inlet and one outlet. We'll have the force is equal to m dot times v out minus m dot times v in. And this is the vector force that we're looking at here. And so since we want to find the force component in the x direction, it's just going to be Fx is equal to m dot times v out x minus m dot v in x. Okay, so that's what we're looking to solve for. But first, we need to figure out what this m dot is and what that tells us about the velocity at the outlet. And so we're going to start with mass conservation. Right? So by mass conservation, we're going to have m dot out equals m dot in, and that's going to be equal to, and let's look at this control surface 1, or this first control surface, because this is going to be the easier place to start. So if m dot out is equal to m dot in is equal to rho, right, our constant density times the area of the jet, constant area of the jet, times, and now this is going to be the velocity of the jet as it's moving in relative to the motion of the cart. Right, so we have our jet velocity coming in at this control surface, and we're going to have to subtract the velocity of the cart from that. And so this is going to be rho times aj times v Vj minus Vc, right? So that's our m dot in, and we know that's equal to our m dot out. And so what this tells us, if we're looking at this control, at this flow across this control surface here, it tells us that the velocity of our jet in our moving control volume, as we're sitting here, moving along at this constant velocity of the cart, it tells us that the velocity at our outlet, the magnitude of the velocity at our outlet here, is also equal to this Vj minus Vc. We'll see that becomes really important in just a second. But first, let's start plugging this in. So we're going to have Fx is equal to, let's start with the Vin term. Okay, so Fx is equal to, we'll deal with this in a second, but the m dot V out, x minus m dot, which is just rho a j times Vj minus Vc, right? That's just m dot, times, and now this is V in. Remember, we're in a moving control volume here. This is V in relative to the motion of control volume, and that's just going to be the velocity of a jet minus the velocity of the car times Vj, Vj minus Vc. And then now for the momentum that's leaving our control volume, again, it's going to be m dot, which is the same expression, so rho times a j times Vj minus Vc. And now we need to find the x component of the velocity that's leaving our control volume. And remember, just a second ago, we said that the velocity that's leaving our control volume, in order to satisfy mass conservation, it has this magnitude of Vj minus Vc. All right, so if we look here at this control surface, we have velocity in our moving reference frame, Vj minus Vc. And now what we're looking for here is what is the x component of this Vj minus Vc, and that's simply going to be Vj minus Vc times cosine theta. So if you look here, we're going to have Vj minus Vc squared times cosine theta. And so now we can combine a bunch of these terms together and simplify this and get to our answer. And so we're going to have Fx is equal to rho times Aj times Vj minus Vc squared, right? Same term on both sides, and then times cosine theta minus 1. And times cosine theta minus 1. And it looks like I've actually made a sign error here. So if we look at this, the force that's applied, the way it's defined in the problem is in the negative x direction. So this is actually negative. And so we end up with Fx is equal to rho Aj times Vj minus Vc squared times 1 minus cosine theta. Okay, so that's our first answer, right, for part A. So now in part B, we're asked to find the power P that is delivered to the cart. So to do that, we're going to note that the power is going to be the force that's applied times the velocity of the object on which you're applying that force. So since we're applying that force onto this cart itself, since we're applying that force onto the cart itself, this is going to be the velocity of the cart. And the force that we're applying is in the x direction, so it's going to be Fx. And so we can substitute in our term for Fx, and we get that our power is going to be equal to rho times aj times vj minus vc squared times 1 minus cosine of theta times the velocity of the car. So now in part C, we're asked to find the force, the cart velocity for which the force Fx is a maximum. And so we can look at that, part C. So now if we look at our expression up here, we want to know what is the cart velocity at which this force is going to be the maximum. We could take the, we could take the derivative of this entire term and try to find out when it's equal to 0, the cart velocity for which is equal to 0. Or in this case, we could just look at it and say, what would I have to do to this VC in order to make this cart velocity, the force applied maximum? And it's, you can see that if we make this cart velocity equal to 0, then we're going to be having to restrain the cart against the maximum, or apply the maximum force against the cart, because this term here is going to have the maximum possible magnitude. And so here we can just say maximum force occurs when Vc is equal to 0. And then finally for part D, now we're looking for the maximum power. And here, things are just a little bit more complicated than they were in part C. So maximum power, for this we're going to find the point where dP dVc is equal to 0. And then we're going to evaluate that in order to figure out what point our cart velocity is, the power that's applied is maximum. And so if we take our term for power from part B, we can say that this power, let's expand it a little bit here. So it's going to be rho aj times 1 minus cosine theta times, we're going to take this term and we're going to expand it out so we can take this derivative just a little bit more easily. And so we're going to have Vj squared times Vc minus 2 Vj Vc squared, carrying over this term from the right-hand side, plus Vc. We're going to get a square term from here, and then we have another term of Vc here. So it's going to be plus Vc cubed. And now in order to find the derivative of this term with respect to Vc, we basically just have to evaluate this polynomial, right? And so we're going to have dP dVc is equal to rho aj times 1 minus cosine of theta times the derivative of this with respect to Vc is just Vj squared. That's going to be minus 4 Vj Vc plus 3 Vc squared. And now we want to set this whole thing equal to 0. And if we set this whole thing equal to 0, this whole term here is going to drop out. So it's equivalent to finding the cart velocity Vc at which this whole term here is equal to 0. And so we end up with Vj, let's rewrite that, Vj squared minus 4 Vj Vc plus 3 Vc squared equal So we're going to factor this out into two separate terms, and we're going to find that we have, um, we can rewrite this as VC minus Vj times 3VC minus Vj is equal to 0. And now if we look at this, we can evaluate, we're going to find that there are two points where dp dvc is equal to 0. The first is where vc is equal to vj, but that is actually going to result, right? So if we look at our problem here, if vc is equal to vj, or if the velocity of the cart is equal to the velocity of the jet, then we're going to have 0 force applied. And so this first one here, rotating this around, this is going to be a local minima. So that means this is the route that we're looking for. And so this is 3VC minus VJ is equal to 0, or so therefore we have 3VC is equal to VJ, or VC is equal to VJ.